Hi everyone, in this video we would like to simulate or put the synchronous machine, asynchronous machine or the induction motor inside the Simulink or using the Simscape. So the first thing we are going to click on new, then we are going to choose a Simulink model in order to simulate our induction motor or the induction machine. So first we are going to use the blank model. Okay, starting the Simulink. So now we have our Simulink. Let's maximize it. So the first thing we are going to use the Simulink library. Then the first thing we are going to search for is the Power GUI. Remember that the Power GUI is the one which is necessary in every aspect. So Power GUI, then enter, then add block to the model untitled. Okay, so we added the continuous Power GUI. So now again to the Simulink library. Then we need to add the asynchronous machine, synchronous, enter. Okay, so let's see the Simulink, Simscape. Okay, the Simscape. So let's see where is the induction machine, asynchronous machine per unit values. Okay, this is our synchronous machine. So this is inside the per unit values. Okay, if you are dealing with the power system, then we are going to use the power unit or the per unit system. But since we need an actual values in order to measure the torque, the speed, and stator currents and everything, we need actual values. Okay, we don't need the per unit. So we'll use the SI units or the standard international units. Click on it, then right click and add block to the model untitled. Now we have here our asynchronous machine. Like here, you will find here it is consisting of 3 terminals A, B, and C. Okay, this is the stator currents, okay, or the stator input currents, and ABC, the rotor currents. And we have here the TM or the torque of the motor. Okay, we here connect our load, and we have M, which is the measurement port. Now, what's the first thing we are going to do? We need to supply our motor. In order to the motor to operate, we need a 3-phase supply. So we can simply, instead of using a 3-phase supply, let's do something different. So let's say voltage source, enter. And let's see the Simscape, of course. Okay, let's see what we have here. We have the AC voltage source, this one. Add block to the model untitled. Now taking this one here, like this, maximize. Now connecting it to here. Okay, this is the first voltage, which is A. So let's say here, voltage source, volt A, voltage, or let's say it VA. Okay, VA is the voltage of the terminal or the first phase, which is A. Now we will select this one and control and drag in order to duplicate it. Like this. So let's move it like this, and this one here, and this one here. Now connect this one here, and connect this one here. So we have VB, okay, VB, and here VC, the 3-phase input supply, and we need to add the grounding. Why? Because we would like to connect this motor as a star. We can use a star connection or use a delta connection. So as an example, we are going to use the star connection. So we need the 3 terminals here connected to the ground. So going to Simulink and typing ground, enter. So we have the Simscape. Okay, we need the Simscape ground, add block to the model untitled. Okay, like this. This is our ground, and you will find that here connecting like this, and this one here, and this one here. Okay, I would like to give you a hint about something. Going to the Simulink, look at this one. You will find here that this one is in the black, and the ground also here in black. So this ground is suitable for the sources here. So you'll find that this ground is from the power library elements ground. Now let's get back to the voltage source, going down. This one is a power library, electrical sources AC. So this one is from the library of the power library. And the ground, this one, is also from the power library. That's why this one can be connected to this one. Okay, because this one is from the power library, and this one is from the power library. Now if we look at this one, for example, FL library, which is not the same library, that's why if we add this one, for example, add the block to the model untitled like this, okay, and try connecting it here, it will not be connected. Why? Because this one is from a different library than this one. So delete this one and delete this one. Now going back, if we look at our synchronous machine, asynchronous machine, look at here, it is power library. Okay, so we have a power library connected to an AC voltage source power library and the grounding power library. Now if we double click on the asynchronous machine or the induction motor, you can find here that we can choose the rotor type. Okay, if it is a wound or a squirrel cage or double squirrel cage or whatever you would like to simulate. So now as an example, if I would like to change this rotor type into another type such as the squirrel cage, okay, for example, now in the squirrel cage you can add a preset parameters, a squirrel cage preset model. So if I click on it, you will find here that we have a different types of the squirrel cage. You will find here, for example, 5 horsepower, 460 volt. Remember that the 460 volt is the RMS and line to line. And the frequency here 60 hertz, and the RPM is 1750. This speed is the rated speed. So we would like to test this motor or this induction motor at a different loading, and we would like to see the stator currents, the rotor currents, the torque or the speed, and everything what will happen inside this induction machine. So as an example, we can choose this one, for example, 5.4 horsepower, 4 kilowatt, 400 volt, 50 hertz, and 1430 RPM. So try to remember this. So we have 400 volt, which is the RMS value line to line. Okay, apply, and 50 hertz. Okay. Now we will find that here, the since it is a squirrel cage, you will find that the three phase here, the three phase currents output disappeared. Okay, and they all combined in one measurement port. So let's see what will happen here. If we double click here, we have a 5.4 horsepower or 4 kilowatt, 400 volt, and 50 hertz. Okay, so going to the phase A, what is the peak value? So as you remember that from the electric circuits, that so in order to change the line to line voltage to phase voltage, remember that we divide for the line to line voltage by root 3. Okay, root 3 is 1.732. Okay, 1.732. So we have a 400 volt divided by 1.732 equal, this is the phase voltage but as an RMS. In order to change this value to the big value, we multiplied by root 2, okay, 230. Let's delete all of this. Okay, I hate this calculator, really I hate it. Root 2 root is 1.414 multiplied by 230 94 equal 026.59. 026. Okay, let's take this one here, copy. 026.59. okay, as I remember. Control C. Now this phase A have a 0 phase shift and the frequency 50 Hertz. Okay, so the big value, okay, we remember that the 400 volt is the line to line and RMS. So in order to change the line to line to phase, divide by root 3. And if we would like to change this phase voltage from RMS to a big value, we multiply by root 2. So okay, this is our first supply. Second one, which is B, same value of the voltage, phase shift minus 120 degree, shifted by 120 degree, and frequency 50 Hertz. Okay, phase number C, 120 degree plus 120 degree, 50 Hertz. Okay, so now we have our three-phase supply. Okay, phase A, phase B, phase C, phase voltage 326, and we have the connected to our induction motor. Now we need to connect the load and we need the measurement. So first, let's see the measurement. In order to get the measurement here, it includes a lot of values of the machine, such as the stator currents, rotor currents, and so on. So how can I do this? First, you are going to select in Simulink library bus creator. Enter. So we have here the Simulink, okay, bus selector and the bus creator. So we are going to select this one, bus creator, add the model to the model untitled and the bus selector. Okay. Okay, let's move them away from each other. Okay, like this. Delete this one and make this one larger. Okay, like this, and maximize this one and move this one here. So what does this do? The bus selector simply connects the measurement to this bus in order to produce an output measurement signals. So if we double click on here, we will understand how it is. Selected signals, select all of this, delete, delete. Now you will find that here, what does the bus selector do? The bus selector simply takes the measurement, okay, which is here signals in the bus. In this measurement, we have the rotor measurement, stator measurement, and the mechanical measurement. Then we can take these signals and produce output signals. So what does it mean? It means that mechanical, select the rotor speed in omega m or in the radian per second and click on select. So we selected first the mechanical rotor speed. This is one which I would like to measure, and the electromagnetic torque, okay, produced. Select. Okay, so we selected the omega or the rotor speed and the torque produced. Now also I would like to select the stator currents A, B, C. Select. Okay, stator current A. Select stator current B. Select stator current C. And for the rotor, I would like to select the rotor current A, rotor current B, rotor current C, and so on. So we have 1, 2, 3, 4, 5, 6, 7, 8 output signals. So we'll see that here, what will happen if I click on apply? You will find here 1, 2, 3, 4, 5, 6, 7, 8. This one, the first one, is representing the first one, which is the mechanical rotor speed. Second one representing the mechanical electromagnetic torque. Third one representing the stator measurement, and so on. So okay, now I would like to measure to see the output torque, and would like to see at the same time the output speed. So going to the Simulink and typing the scope, okay, scope, right click, add block to the model untitled, and the display, okay, display, enter. We have the display, add the block to the model untitled. Okay, move this one here, move this one here. Now look, this one mechanical rotor speed, then mechanical torque, then stator IA, IB, IC, and rotor IA, IB, IC. So we can select the first one, which is the mechanical speed, okay, and see it here. Okay, remember that this speed is omega m, mechanical speed in radian per second. And if you see here that the speed here in 1430 rpm, so I would like to change the radian per second to rpm. So how can I do this? Remember that the speed itself, the omega is equal to 2 pi n over 60. Okay, we explained this before, 2 pi n over 60. So in order to change from omega to n, we will multiply the omega by 60 over 2 pi. So going to the constant, okay, or the, not the constant, but the gain, okay, then right click, add block to the model untitled, take this one here, take this here, and then move this one, delete this one, take this one here, and then here, then double click. Okay, this one to convert the omega m into the n or the rpm. So multiply by 60 over 2 pi. Okay, okay. So this will convert the rotor speed to the rpm or the revolution per minute. So this one is the speed, okay. Take this display here to see what will happen to the speed. Now what is the next step? Okay, the next step is that we need to add the electromagnetic torque, similar as before. So we need a scope and we need a scope and we need the display. So control and drag. Then we are going to take this one here and take this one here. Here, torque. Okay, so we have display, torque. This is a three-phase stator current, three-phase rotor current. So what will happen here? Here, okay, let's select this one and make it like this. Okay, so what does the bus creator do? The bus creator simply combines the signals together. Okay, combines the signal together. So double click on this one and make the number of inputs 3. Okay, you will understand now why. Okay, like this, and control and drag. Okay, so we have the three-phase rotor current. I would like to display them together, and the three-phase stator current, I would like to display them together. So take this one, stator current IA, IB, IC, and rotor current IA, rotor current IB, rotor current IC. Okay, so we have 1, 2, okay, everything. Now the stator currents and the rotor currents. Now I would like to display all of them in one scope. So I will take 2 scopes here. Okay, control and drag. Now we will take for each of these scopes, okay, current 1 or stator current, and the rotor current 2, okay. Then take this one here and take this one here. Now we have the display for the electromagnetic torque, rotor speed, and we have the scope for each of the currents. Now we would like to add our torque. So our torque is simply, let's see the machine itself. We have a 4 kilowatt. This is the maximum output power. So let's go to the calculator again. Then first we would like to see what is the maximum output torque. So the power, which is 4 kilowatt, 4 multiplied by 1000, which is 4000 of course. The power over the speed, which is 2 by n over 60. Okay, so let's see 2 multiplied by pi, which is 3.14. okay, 3 multiplied by 3.14 multiplied by 2 pi n, okay, n which is 1430 over 60. This is the rated omega. So 2 by n over 60, and take this one multiplied by 4000. 4000 divided by 149.67333. So it will give us the maximum torque to be 26.72. So 26.72. okay, remember this value, which is the maximum torque. So what we are going to do in this step, so first we are going to use a step, okay, step in this step. Add block to the model untitled. Okay, take this one here. We need to produce a variable torque, so we are going to put a different torques at a different times. So what I mean by this, let's see, we will take 4 conditions. Okay, so we need 4 steps. Like this. Okay, so this one step at 5 seconds, 5 seconds. This step at 10 seconds, 10 seconds. This one at 15 seconds. This one at 20 seconds. Okay, so the first one, which is at 5 seconds, initial value 0, and final value is 26.72. okay, 26.72. so this one is the initial load, which is the maximum torque. Now we are going to add a summing node. Okay, so for the summing node we will type sum, enter, then add block to the model untitled. Okay, take this one here. Okay, what I'm doing, I don't know, delete, then maximize. Okay, come here, maximize, double click, plus, minus, minus, minus. Okay, so we have 4 conditions. The first one is the maximum torque applied, so it is a positive value. So add this one to this terminal. Okay, so at 5 seconds, at the time of 5 seconds, we are applying the maximum torque of 26.7. Step time, okay, the step time, okay, is 5 seconds. And the initial value is 0, and the final value is 26.72. Okay, so at this instant, the maximum torque will be applied. At a 10 second, I would like to reduce this torque to half its value. So in order to put the half divided by 2, 13.36. okay, 13.36, I think, 36. Okay, so at a time of 10 seconds. So at a time of 10 seconds, we will apply the 13.36, but with a negative value. So we have originally 26, and we are applying 13 with a negative value. So the total of them will be 13. So we are reducing the torque. Okay. Now at 15, I would like to reduce it to the quarter. Okay. So going to the calculator, divide by 2 again, 6.68. Okay. So what will happen at a time of 15, the total torque will be the quarter. And this one will be also 6.68 in order to make the torque becomes 0. 6.68. Okay, so what happens here? Okay, take this one here like this. At a time of 5 seconds, we apply the full load torque. At a time of 10 seconds, we will reduce this torque by quarter its value. At a time of 15 seconds, we will reduce another quarter. Okay, so we reduce here half of the torque, and here we reduce the torque to its quarter, its value, and here we reduce the torque to 0. Okay, so full load, full torque, half of the torque, quarter of the torque, 0 torque. So we would like to see the change inside the torque itself. So we need a scope. Scope. Like this. And TL, or the load torque. So we would like to simulate this for 20 seconds. Okay, or 25 seconds. Okay, more than the time. Now we prepared everything here. We added the measurement for the torque, the speed, the currents, and everything. Now we would like to start simulating this and see what will happen when we start simulating this torque. Now after simulating the program, you will find that here for the rotor speed, finally we have a 0 torque. So as you remember from the synchronous machine of 1430 RPM, this speed is the rated speed, okay, the speed at full load. So at no load, the speed is nearly equal to the synchronous speed. Okay, as we remember from our explanation for the induction motor, we said that the speed at no load nearly equal to the synchronous speed. The synchronous speed is 1500. So 1499 is acceptable. The final torque value is 0.4686, which is a very negligible value of torque. Very small value for torque. Now let's see what happened to the rotor speed. Opening the speed. At the beginning, at no load, the speed was nearly equal to the synchronous speed, which is 1500 RPM. At 5 seconds, what happened? At this instant, we applied the full load torque. So the speed goes down to 1430. Okay, the speed or the rated speed of the motor itself. Then at a time of 10 seconds, we reduce the load by half of it. So find that the speed increased again. Then at 15, we reduced the speed, the load to the quarter. So the speed increases again. Then at 20, we removed the total load, so it increased to the final value. And you'll see that here, there are some transient due to the change of load. Now for the torque itself, at 0 output torque, nearly 0 output torque, then we apply the load, which is 26, so it increased to 26. Then we at 10 we reduced it to half of it, 13. Then at 15 we reduced it to the quarter, which is 6.6. and to the 20 we remove the total load going back to 0. Now the current, okay, the stator currents, you will find here that the stator currents at the beginning was little. Then at 5 seconds, when we increased the torque to the full load torque, you'll find that the stator current increased because we absorb more current in order to produce the torque. Then at 10 we reduced it to half, so the current is reduced to half. The 3-phase current reduced to half. Then at 15 reduced to quarter of the load. Then at 20 we removed the total load. So we'll find here that this is the minimum current, maximum current at full load. Then it starts to decrease as the loading decreases, okay, because we absorb more current when the load increases. Now saying here the rotor current, at no load, 0 current, okay, the rotor does not have any current because we don't have any load right now. At full load, the 3-phase current is produced. Okay, high 3-phase current produced due to the presence of load. When we reduce the load, the torque, the current is reduced from the full load torque. Then it reduced again at the quarter, then it is 0 at no load. Now watching the load torque, 0. At 5, it changes to 26.7. Then at 10, reduced to half. Then at 15, reduced to quarter. Then at 20, reduced to 0. Now we'll find here, this is a display for the rated speed, the final rotor speed, and this one is the final torque at no load. Now, if I would like to see the change in these values during the simulation, what can I do? Simply we'll go to this one, which is a step back, okay, or stepping back option. Enable stepping back. Then we can maximum number of saved back steps, 10 steps, okay, interval between stored steps. We can use 5 or let's make it 3, for example. Okay, now watch the values here while doing the simulation. You will find here the values is changing during the simulation of the time. So you see the variation in values during the simulation. So this is how to simulate the induction motor or asynchronous motor or asynchronous machine inside the MATLAB Simulink.